Good morning, class 3 of Unit 4, solid state control of synchronous motor drive. So, till last class we discussed speed control of three-phase synchronous motor drive. So, the next one, control of synchronous motor drive using variable frequency supply. So, we know the basic relation between synchronous speed and supply frequency, Ns should be equal to 120F divided by P. So, the synchronous speed is directly proportional to supply frequency. So, at the time of rated voltage and rated frequency, the synchronous motor drive is operating under base speed. So for high speeds, the motor is operated at rated terminal voltage and variable frequency supply. So while increasing variable frequency supply, the pull-out torque going to decreases. So the pull-out torque is inversely proportional to variable frequency supply. So to control the synchronous motor drive using variable frequency supply, we have the two methods. One is true synchronous mode or separate controlled mode. Second one is self-synchronous mode or self-controlled mode. So when we are using multiple number of synchronous motor drive control, we have to use the separate controlled mode. When we are doing single synchronous motor control, we have to use the self-controlled mode. So we go and discuss briefly about these two methods one by one. The first one, true synchronous mode or separate controlled mode. The name itself is shows we have to use the separate external frequency signal to control the synchronous motor drive. In separate controlled mode, the state of frequency signal is controlled by independent of oscillator. It means the frequency is changing from initial to desired value. At the same time, the difference between the synchronous speed and synchronous motor rotor speed is very small. I mean the difference between the both speed is very less. So when the synchronous motor reaches the desired synchronous speed, so the rotor moves to the synchronism. So at the same time, while operating under separate controlled mode, the number of hunting oscillations are more. So to eliminate the hunting oscillations, we are using the damper winding. So at the same time, while using variable frequency control, it's not only allows the speed control, also provide smooth starting and regenerative braking. So see this block diagram. So it clearly shows how the separate control mode of operation done for synchronous motor. So first see here in terms of open loop operation. So AC supply is given to the rectifier. So the rectifier is going to convert AC into DC. So that DC having the number of ripples. So to remove that ripples, we are using LC filter. So with the help of this LC filter, the ripples are removed. Then the DC is given to the inverter circuit. So the inverter going to convert DC into AC voltage, variable frequency. So it's given to the multiple number of synchronous motor drive. So here for generating the switching pulses for rectifier and inverter, we are making closed loop operation. So it's nothing but, so here we are taking a external separate frequency signal. So with the help of delay circuit, we are giving to the VSI inverter. So on one more block, the flux controller. So with the help of flux controller, we're going to convert frequency parameter into voltage parameter. So by comparing the two voltage signals with the help of firing circuit, we're going to generate the firing pulses to the rectifier circuit. So now, so it's called as true synchronous mode or separate controlled mode. So here we are using separate external frequency signal to control the synchronous motor drive. That's why it's called separate control mode. So mostly the separate control mode utilized for multiple synchronous reluctance motor or permanent magnet motors. So for real-time applications like fiber spinning mill, textiles and paper mills and all, we are using separate control mode of operation for synchronous motor drive. The second method is called self-synchronous mode or self-controlled mode. It's nothing but, so the frequency signal is generated from the own machine, I mean actual machine. From the actual machine, we're going to measure the frequency signal. So with the help of that frequency signal, we're going to control the synchronous motor drive. That's why it's called self-synchronous mode or self-controlled mode. See the block diagram. So the three-phase AC supply is given to phase control rectifier. So the rectifier is going to convert AC into DC voltage. So that DC voltage is given to inverter. I mean the static converter is called as inverter. So the inverter is going to convert DC into AC. So it's connected with single synchronous motor. So the self-control mode is only applicable for single synchronous motor drive. So now we're going to measure the frequency as well as speed signal from the synchronous motor drive using shaft encoder. So with the help of that frequency signal, so we're going to compare with the reference speed and actual speed, and reference frequency with actual frequency. So with the help of control circuit, I mean firing circuit, we're going to generate the firing pulses for the rectifier and inverter circuit. So it's called self-controlled mode or self-synchronous mode. So from the motor itself, we are generating the both speed. I mean, we are measuring the actual speed and actual frequency. So with the help of that actual frequency and actual speed, we are doing the control. That's why it's called self-controlled mode or self-synchronous mode of operation. So you can see the comparison between self-control and separate control mode. So in separate control, I already told, so we are having the hunting of oscillations are present. So to remove that, we require the damper winding. In self-control mode, so no hunting is there, so no need of damper winding. So at the same time, so here we have to use a separate external independent oscillator to control the synchronous motor drive. Separate frequency signal is required. But in self-control mode, no need of separate or independent oscillator frequency signal is not required. So then the fourth one, multiple number of machines can be controlled here, but here only single machine is controlled for self-control. So the next same, the self-control and separate control, going to discuss with in terms of VSI inverter. So we already know VSI inverter having the two types. One is square wave inverter, another one is PWM inverter. So in the unit 3 itself, we discussed about square wave inverter and PWM inverter. So generally, the square wave inverter can able to generate single output waveform for half cycle. But in terms of PWM inverter, so depends upon the user, we can able to generate multiple number of output waveforms. I mean by giving multiple number of gating signals. But in square wave inverter only we can able to generate single gating signal or single switching signal for half cycle. Based upon only half waveform can be generated per cycle. So now we're going to discuss both separate and self-control mode in terms of square wave inverter and PWM inverter. So first we're going to discuss about separate control. So under separate control of synchronous motor drive, fed square wave inverter. The inverter type is a square wave inverter. So the applied input signal is a three-phase supply is given to rectifier. Rectifier going to convert three-phase AC into DC. So the ripples in the DC can be eliminated with the help of LC filter. So it's given to in square wave inverter. The square wave inverter going to convert DC into AC. So the AC is connected with synchronous motor drive. So the difference is here, the square wave inverter means it can able to generate only single output waveform per half cycle. If it is PWM inverter, it can able to generate multiple number of output waveform even in a single half cycle. It's a basic difference between square wave inverter and PWM inverter. So we already know it's a separate control mode. So we have to use a separate frequency, external frequency signal to control, I mean to generate the firing pulses for the inverter and rectifier. So with the help of separate external frequency signal, we are generating the firing pulses for the rectifier and inverter cycle. So it's called separate control mode of synchronous motor drive using square wave inverter. Next same separate control of synchronous motor drive with PWM inverter. So the same cycle three-phase supply are giving with the help of rectifier, it's converted AC into DC. So the ripples are removed with the help of LC filter. Then it's given to PWM inverter. So the PWM inverter going to generate multiple output waveforms in a single half cycle. So it's connected with synchronous motor drive. So it's separate control. So obviously you are using external frequency signal to generate the firing pulses for the inverter as well as rectifier. So in terms of inverter structure is common for both square wave inverter and PWM inverter. The number of switches used in the inverter is same, but only the difference is how we are giving the firing pulses or switching pulses to the particular inverter. So if you are giving multiple number of firing pulses per half cycle, it can able to generate multiple number of output waveform per cycle in PWM inverter. Suppose we are giving only single switching pulses or the inverter means it can able to generate only single output waveform using square wave inverter. So only the PWM inverter or square wave inverter difference based upon the switching pulses applied. In terms of structure wise, both are same. Next one, the same one in the previous two are discussed based upon separate. Here the self-control of synchronous motor drive using square wave inverter, the same circuit. So three-phase AC is given here to the rectifier. It's going to convert into DC. So the ripples are removed with the help of LC filter. So then it's given to square wave inverter. So the square wave inverter able to generate single output waveform per half cycle. So it's connected with synchronous motor drive. So for controlling this inverter and rectifier, we are measuring the frequency and speed signal from the motor itself. I mean from the actual frequency and the actual speed is measured from the motor. It's given, even it's taken into the account for generating the switching pulses for the rectifier and inverter cycle. So that's why it's called self-control mode of synchronous motor drive. Next one, self-control mode of synchronous motor using PWM inverter. So here the three-phase AC is given to the rectifier. It's going to convert AC into DC. The ripples are removed using LC filter. It's given to PWM inverter. So the PWM inverter can able to generate multiple number of output waveform depends upon the switching pulses applied. So at the same time, the inverter is here the rectifier is a diode rectifier, so no need to give any firing pulses for the rectifier. But for the inverter, we have to generate the switching pulses. That switching pulses depends upon the actual parameters. I mean the speed parameters measured from the synchronous motor drive. That's why it's called self-control. The next one, chopper fed synchronous motor drive. So with the help of chopper circuit, how the synchronous motor is controlled. The same, see the block diagram. So the three-phase AC supply is given to the diode rectifier. So it can able to generate AC into DC. So that DC is a fixed DC. To convert into variable DC voltage, we are using the chopper circuit. So this chopper circuit is a voltage commutator chopper. So with the help of this voltage commutator chopper, we are converting fixed DC into variable DC. Then for removing the ripples present in the DC, we are using LC filter. So the output of LC filter is connected to square wave inverter. So the square wave inverter can able to generate the output waveform, stepped output waveform. It's given to the synchronous motor drive. So here with the help of this chopper circuit, we are controlling the synchronous motor drive. So it's called as chopper fed synchronous motor drive. So next one, VSI fed synchronous motor drive. So we already know the VSI inverter, voltage source inverter having the two types. One is PWM inverter and one is square wave inverter. So the VSI fed drive can be also developed to have the self-control using rotor position sensor or phase control methods. So but normal voltage source inverter with 180-degree mode of conduction of thyristor require forced commutation or load commutation. So here it's not possible. So for that purpose, we are using three combinations to provide a variable voltage and variable frequencies applied to control the synchronous motor drive. So that three combinations are: first one using PWM inverter and diode rectifier, second one using square wave inverter and phase control rectifier, third one using square wave inverter, chopper and diode rectifier. So we'll discuss all these three combinations one by one. First one using PWM inverter and diode rectifier. So the three-phase AC is given to diode rectifier. So the diode rectifier going to convert AC into DC. So with the help of LC filter, the ripples are removed in the DC supply. So the DC is given to PWM inverter. So the PWM inverter going to generate multiple number of output waveforms, stepped output waveforms. So it's connected with the synchronous motor drive. So using PWM inverter and diode rectifier, we are controlling the synchronous motor drive. So next one using square wave inverter and phase control rectifier. So three-phase AC is given to phase control rectifier. It's convert AC into DC. So with the help of LC filter, we are going to remove the ripples present in the DC. So the DC is connected to the square wave inverter. The square wave inverter can able to generate, I mean, it's able to convert fixed DC into variable AC. So it's connected with the synchronous motor drive. So the square wave inverter can able to generate single output voltage waveform per cycle. So the switching pulses applied to the both phase control rectifier and square wave inverter is controlled with the help of external firing pulses. Next one, using square wave inverter, chopper and diode rectifier. So three-phase AC is given to diode rectifier. It's going to convert AC into DC. So for converting fixed DC into variable DC, we are using the voltage commutator chopper here. So it's converting fixed DC into variable DC. So to remove the ripples present in the DC, we are using LC filter. Then it's connected with the square wave inverter. So square wave inverter can able to generate single output waveform for half cycle. So it's connected with synchronous motor drive. So that's why it's called square wave inverter based chopper and diode rectifier for synchronous motor drive control. So here under separate control and self control itself, we are having VSI fed synchronous motor drive and CSI fed synchronous motor drive. So we'll discuss one by one. So self-controlled VSI fed synchronous motor drive using square wave inverter. So the title itself we can give the clear meaning for that. So self-controlled, it means we're going to measure the various parameters like speed and frequency from the motor itself. Then VSI fed synchronous motor. VSI fed, under VSI we are using square wave inverter. So it can able to generate only single output, stepped output waveform per half cycle. So now see the diagram. So three-phase AC is given to phase control rectifier. AC going to convert into DC. So now to remove the ripples present in the DC, we are using LC filter. So the output of LC filter is given to square wave inverter. So with the help of the square wave inverter, we going to generate single stepped output waveform per half cycle. So the output of square wave inverter is connected with synchronous motor drive. So this one is a self-control. So we're going to measure the frequency and speed signal from the synchronous motor drive. So it's given to the firing cycle. The comparisons are happening there. So with the help of that, we are generating the firing pulses for inverter as well as phase control rectifier cycle. Next one, self-controlled VSI fed synchronous motor using PWM inverter. Same like a previous circuit, only the inverter is changing. In the previous one, square wave inverter, here PWM inverter. So we can able to generate multiple number of output waveform per half cycle. So it's connected with synchronous motor drive. So obviously it's a self-control. So we have to do the firing pulse generation with the help of self parameters. I mean, the frequency and feed signals are measured from the motor itself. Next one, separate controlled VSI fed synchronous motor drive using PWM inverter. So the name itself is separate control. So obviously we're going to use a external speed and frequency signal to generate the firing pulses for the inverter circuit. So three-phase AC is given to diode rectifier. AC is converted into DC. So with the help of LC filter, the ripples are removed. So then the DC input is given to PWM inverter. So with the help of PWM inverter, we can able to generate multiple number of output waveforms per half cycle. So it's connected with multiple number of synchronous motor drive. We already discussed in the difference between self and separate control mode. In separate control mode, we can able to control multiple number of synchronous motor drive. But in self control, only we can able to control single synchronous motor drive. So here the firing pulses for the PWM inverter is separately generated with the help of external frequency and speed signal. Next one, separate control of synchronous motor drive using square wave inverter. Same like a previous block diagram, only the change is a square wave inverter. So the square wave inverter can able to generate single output waveform per half cycle, stepped output voltage waveform. It's connected with a synchronous motor drive. So here also we are controlling multiple number of synchronous motor drive. The reason is it's a separate control mode. The last one, self-controlled CSI fed synchronous motor drive. So here the using the inverter type is a current source inverter. So it's a self-control. So obviously we're going to measure the parameters like actual speed and frequency from the motor itself, which is compared with the reference speed and reference frequency. So based on that, we're going to generate the firing pulses for the rectifier and inverter circuit. So now the three-phase AC is given as an input voltage to the rectifier. So the AC is converted into DC with the help of rectifier circuit, phase control rectifier circuit. Then with the help of L filter, we're going to remove the ripples present on the DC voltage. Then the DC output voltage is given as an input for the CSI inverter. So CSI inverter going to convert DC into AC. So the AC is connected with synchronous motor drive. So here we are using single synchronous motor drive. The reason is the control is a self-controlled mode. So with the help of rotor presence sensor, we are measuring the speed signal for generating the firing pulses for the rectifier and inverter circuit. By comparing the actual speed and set speed, we are getting error speed value. From that speed value, we are generating the switching pulses for rectifier and inverter circuit. So this are so that's all about self-control and separate control of synchronous motor drive. So these are the two main control methods for synchronous motor drive using variable frequency supply. So in the next class, we'll discuss about closed loop operation of synchronous motor drive and cycloconverter fed synchronous motor drive and power factor control for synchronous motor drive. In the next class, we'll discuss. Thank you.